The Myhill-Nerode theorem and the method of test sets. The Myhill-Nerode theorem is due to Nerode, although Myhill has a similar result. See the historical notes at the end of the section. The Myhill-Nerode theorem is a beautiful purely algebraic characterization of the computational notion of having a finite automaton accepting a language. The characterization has no reference to computation or dynamic notions such as regular expressions. The theorem is of great importance in terms of practical algorithms for minimizing the number of states in a finite automaton. As we will see when we look at the method of test sets, the Myhill-Nerode theorem is also of importance in constructing automata for regular languages with only implicit computational descriptions, rather than explicit ones, such as being specified by a regular expression. This later property will be used extensively when we look at graphs where often all we have is such an implicit description. However, first we will need the theorem. Definition 6.20. Right congruence. A. We call a relation R on a set sigma star a right congruence with respect to concatenation if and only if 1 R is an equivalence relation on sigma star. 2. For all x, y in sigma star, x or y if and only if for all z in sigma star, x, z or y, z. B. For a language L, the canonical right congruence induced by L is the relation congruence L defined by X congruence L y if and only if for all Z in sigma star, X, Z in L if and only if Y, Z is in L. Intuitively, right congruences must agree on all extensions. Similarly, we can define a left congruence by replacing x, z, or y, x in the definition 6.20 by zx or zy. Finally, we say that R is a congruence if it is both a left and a right congruence. An equivalence relation on sigma star is said to have a finite index if it has only a finite number of equivalence classes over sigma star. Theorem 6.21. The Myhill-Nerode theorem. A. The following are equivalent over sigma star. 1. L is finite state. 2. L is the union of a collection of equivalence classes of a right congruence of finite index over sigma star. 3. Congruence L has a finite index. B. Furthermore, any right congruence satisfying 2, that is, L is the union of a collection of equivalence classes of a right congruence of finite index over sigma star. So any right congruence satisfying such condition is a refinement of congruence L. Proof from 1 to 2. Suppose that L is regular and is accepted by the deterministic finite automaton M equals to the tuple K sigma S F delta without the loss of generality. Let S equals to the set Q0. We define R equals to Rm via X R Y if and only if there is a Q in K such that Q0X yields in the next step start to the tuple Q lambda, and the Q0Y yields in the next step start to Q lambda. That is, on input X or Y, we finish up in the same state, Q. It is evident that Rm is a right congruence since for all Z in sigma star, Q0XZ yields star to QZ, and Q0YZ yields star to QZ. Also, the index of Rm is finite since there are only finitely many states in K. The theorem follows since L equals to the union of the set of row in sigma star such that Q0 row yields immediately star to the tuple Q lambda with any Q in F from 2 to 3. The proof from 2 to 3 is that we prove B from which 2 to 3 follows. Let R be a right congruence of finite index so that L is a union of some of R's equivalence classes. By the fact that R is a right congruence for all Z, XZ in L if and only if YZ is in L, part B follows immediately from this. From 3 to 1, assume that 3 holds. Then we have the following implicit description of a deterministic finite automaton M accepting L. 1. The states of M are the equivalence classes of congruence L. 2. The initial state lambda, the set lambda congruence L, the equivalence class of lambda. 3. The transition function delta of M is defined by delta of the set AX equals to the set AX for A and X in sigma. 4. The accepting states of M are those X with the set X which is a subset equals to L. Notice that item 3 is well defined as congruence L is a right congruence. The point is that congruence L being a right congruence makes the definition of delta independent of the particular representative of the equivalence class. If A is congruence L to B, then delta of the set AX equals to the set of AX equals to the set of BX equals to delta of the set B and X. We see that L equals to L of M, and this concludes our proof. We remark that it is possible to use the Myhill-Nerode theorem directly to establish that certain languages are finite state. Example 6.23 is an illustration of such use of the Myhill-Nerode theorem. First, we need a definition. Definition 6.22. Myhill's congruence defined X double congruence L to Y to mean that for all U and V in sigma star, U X V in L if and only if U Y V in L. It is easy to prove that double congruence L, the Myhill congruence L, has finite index if and only if congruence L has finite index. Example 6.23. If L is finite state, so is the reverse L reef of L. To see this, define X or Y to hold if and only if X to the reef is Myhill congruence L to Y to the reef. As Myhill's congruence L is an equivalence relation, so is R. Furthermore, by the Myhill-Nerode theorem, congruence L has finite index, and hence Myhill congruence L has finite index. This implies that R has finite index. Finally, to see that R is a right congruence, suppose that X, R, Y, and Z is in sigma star. Now X to the reef, Myhill congruence L to Y to the reef, and since the Myhill congruence L is a left congruence, we have that Z to the reef followed by X to the reef is Myhill congruence L to the Z to the reef followed by Y to the reef, and hence XZ to the reef is Myhill congruence L to YZ to the reef. This implies that XZ are YZ, and hence R is a right congruence. Our result will then follow from the Myhill-Nerode theorem once we can establish that L to the reef is a union of equivalence classes of R. We need to show that if X are Y, then X in L to the reef implies that Y is in L to the reef. If X is in L to the reef, then X to the reef is in L. If x r y, then x to the reef is Myhill's congruence L to y to the reef, and hence y to the reef is in L, which implies that y is in L to the reef. In exercises 2-4, we invite the reader to apply the technique of example 6.33 to other languages. Another place we can use the Myhill-Nerode characterization is to efficiently demonstrate non-regularity of languages by exhibiting infinitely many equivalence classes for the congruence L. This technique is often significantly more elegant than classical approaches using the pumping lemma. Corollary 6.25 and exercise 8. Here is an example. Example 6.24. We will demonstrate that the language L equals to the set AN, Bn, such that n is greater than 1, is not regular, using the Myhill-Nerode theorem. For any n less than m, an which is not congruence L to a to the m, since an bn is in L, yet am bn is not in L. Hence, the congruence L has infinite index, and therefore L is not regular. In fact, the classical pumping lemma is an easy consequence of the Myhill-Nerode theorem, as we now see. Corollary 6.25. Pumping lemma. Bohr, Hillel, Perles, and Shamir suppose that L is regular and infinite. Then there exist strings x, y, and z such that for all n which is greater than or equal to 1, x followed by y to the n followed by z is in L. Proof. Define a collection C of streams inductively. Let y0 equals to lambda and yn plus 1 denote the lexicographically least stream extending yn such that the size of the length of yn plus 1 equals to n plus 1. And 2, yn plus 1 has infinitely many extensions in L. By the Myhill-Nerode theorem, there exists n less than m such that yn congruence L to ym, that x equals to yn and ym equals to xy, and suppose that ymz is in L. Then by the Myhill-Nerode theorem, for all k, x followed by y to the k followed by z is in L. We remark that the classical proof of theorem 6.25 is given in exercise 8. Observation 6.26. The method of test sets. The proof of 3 in theorem 6.21 gives rise to what we call the method of test sets. Suppose that we have a language L which we know is regular, but we are not given a regular expression for L, only a representation via a decision procedure for membership via, say, a Turing machine. Is it possible to deduce an automaton accepting L? Using a simple coding argument, we see that the answer is no. Observation 6.27. In general, there is no algorithm to deduce an automaton for a regular language from a machine description